Thank you very much. And I once again would like to thank Riddhi for all efforts and all his colleagues. It's a very pleasant stay. So I'm going to talk about the following model. So the original model, which I will be focusing later, was introduced in 1980 by Rosenstock and Marquardt, and it's aggregation model on ZD. So like most of you already know DLA, and it was notoriously popular in the 90s, etc. But actually aggregation models were looked by various areas of physics, in particular physical chemistry starting from 1930. So the community was there. And then somehow some very beautiful results, of course non-rigorous, were obtained. And they got into mathematical physics community by middle of 60s. No particular progress was done on more rigorous result on the side, but there were many, many beautiful and inspiring articles until it came to late 70s, when sort of thanks to computing technologies appear. So people start to simulate much more precise, etc. And then it was discussed by many authors already in different community, which is mathematical physics community and also computational physics. So model of Rosenstock and Marquardt is the following. You can take ZD, so they were talking actually about Z2, but their definitions are valid for any ZD and actually for any kind of nice graph if you wish. So how we start? So we start with at time zero with particles. So this is original Marquardt model. So particles distributed according to product Bernoulli measure. Because afterwards I will move to Poisson measure. So Bernoulli measure parameter mu, which is between 0 and 1. And you condition that there are no particle at the origin. So it's, and then at the origin you place special particle, which is called seed of aggregate, which aggregate is going to be sort of diffusion limited aggregation prototype. So non-aggregated particles, which are again distributed initially as Bernoulli, when dynamics start to move, these particles move as continuous time simple random walks, obeying exclusion rule. So what Rosenstock and Marquardt wanted, that you have no more than one particle per site. Now, they are moving as random walkers, obeying exclusion rule. So if particle wants to jump on the site where it's already particle, it's rest. And then what happens, the aggregate grows by attaching particles to its surface whenever particle attempts to jump off it. And there is a little star here, I don't know if you see, and I have to say something at this point. So there will be two cases. So this is exclusion case. So here's picture. I can draw it in dimension 2. Of course, even in dimension 1, it's interesting case. So you have special seed, special particle placed at the origin, which doesn't move. And then you have other particles placed as Bernoulli at certain density. And they're moving as random walks, obeying exclusion rules. And then when particle comes next to the red particle, it can leave, go ahead. But if particle wants to jump on the red, it's incorporated and red cluster is growing. Okay. And it goes. So particles are moving, they're coming. Particle came here, wants to move away, moves, wants to jump on red aggregate, it grows, right? And then detail, so this is essentially what is written, but one important rule which is not written there, it happens like that. You may have white particle here, which is not attached to aggregate. And you have another particle which is here, and maybe here, cluster of particles which are moving. And then some particle comes and enters here, and then decides to jump over at aggregate. So whom you attach? So there is cluster of this particle in principle. So we attach only one particle. We don't attach particles which are not attached at the moment of the jump. So otherwise you can produce avalanches, and at low density of particles, doesn't bring headache. But at high density you may have pass, and then this story ends kind of quickly without any interesting situation. So this is exclusion case. So what is interesting, I'm sure not, let's fix for today talks continuous time, but in principle, if I insist on this rule, then you can take discrete time, except you have to be careful how do you update system in discrete time. So particles, and this is not because of aggregation, but because exclusion rule. Then you have to decide, how do you check from configuration to configuration using exclusion rule. But in principle, this is not really technically matters. It brings some technical difficulties. So this model, interesting, I found it, discovered kind of, that model of Rosenstock and Marquardt, when they published it, actually, it was discussed starting from '78. It was considered too difficult. So in order to simplify this, Witten and Sanders said, why we have infinitely many particles? Let's do one. And that gave birth to famous DLA. But famous DLA came out of this model as simplification. And actually, I suggest it's not in my reference, but I can send. There is an article of Sanders, which kind of article when he describes how he sit down over the night, and he looked at only one particle, and he didn't believe that anything interesting will happen. So he bought new computer, and then he was very surprised that by morning time, suddenly this structure which he simulated on computer was not a ball. He expected something like Eden-type growth here, and then this classical DLA is a consequence of simplification of this model. Okay, so this version uses exclusion rule of particles, original version, and it's going to be a main topic of work. But now you also can look at modification of this model. No, you need to work, of course, but it's well defined given, say, suppose you have continuous time, so you don't have any problem of kind of defining dynamics. So at any given time, you have particles, you color them blue and red for aggregate. So aggregate is growing, right? Blue particles which are around you, they don't even know that aggregate exists. Okay, so for blue particles, given that they don't know that aggregate exists, everything is fine, right? So in this sense, a problem of well-definedness is exactly hidden in this rule. If you have aggregate, some kind of cluster of particles at some given time, it could be discrete or continuous, but it's not attached to aggregate. So it just happens that your dynamics of exclusion particles construct some kind of cluster, and then whom you attach. So this is the point where you need to decide. And for example, this process defined by Rosenstock and Marquardt, somehow because of DLA took so huge attention of people, was somehow forgotten and was rediscovered by Voss, a German numerical physicist, who studied all possible ways that you attach all cluster. If somebody cluster is not attached, but somebody comes in the middle and you attach all this. So, but actually, he didn't even know that Rosenstock and Marquardt already did this. But this is only delicate point where dynamics should be defined properly. Otherwise, there is no deep kind of troubles. Okay. Okay, modification. So I drop exclusion rules. So when you have exclusion, density of particles, of course, is between 0 and 1, right? Now I allow particles to move a simple random walk, no exclusion, okay? So in red, you see this modification. Then initially, I can distribute particles according to Poisson measure with parameter rho, which rho now can be from small to as large as you want. And then particles move as continuous simple random walks. Okay? Again, there are two stars here. Aggregate goes by attaching particles. But now you have multiple particles on your side, possibly, right? And again, so this random walk version. And to be clear about dynamics, again, you have seed or cluster, I don't draw this, and then could be that some random walker came here, sits just next to the cluster, but still didn't manifest wish to jump on the cluster. He just said, in principle, in the next step, he could go away. He's not obliged to be glued. And then another particle. So you may have multiple particles here sitting, so any number n is allowed, right? And then one of these particles suddenly, when you have n seated on this side, decides to jump. What you do? You incorporate everybody. All n particles, all this little pile, becomes part of aggregate. It moves only by one vertex. But in principle, if you look at this frozen configuration, aggregate, it contains pile of particles. All of them are incorporated. Okay? And the rule, if you have, as here, if you have some other particles sitting here, they're totally free. You don't incorporate cluster of this advanced particle. Okay? So there are two models, and I will be talking about both of them because techniques are different. We still believe they behave the same somehow. But to prove something from one to another, it differs quite a lot. Okay. So first of all, observation number one, that usual fusion limited aggregation, when you launch one particle per time, there is no real time, it's steps that is called. You have one particle, you launch, it travels, glues. Then when it's glued to aggregate, then you launch another particle, so time is not really question for us. It's question shape and what you see after n steps. Okay? So usual DLA in one-dimensional case presents no kind of suspense. It's kind of just say D equals 1, DLA. Nothing interesting because suppose you can see one-sided, so particle grows, and you have just aggregate growing as a strip. That's it. But this model has very interesting behavior in one dimension, because now what happens, I call it modified DLA. Both in case of exclusion or in case of random walk, which I will talk more because it's interesting, it's already something non-trivial. Because you have initial seed, and now you have multiple particles, infinitely many. They walk either as random walk with exclusion rule or without exclusion rule, and then things start to happen. You get stick, another particle came. In exclusion rule, of course, let me call geometry of the growing aggregate is still simple because it's just strip, because it's only one particle per time. But imagine you have a random walk case. This slide dedicated to random walk. You see that particles can come in multiple and be aggregated like that, and like this, and maybe 3 particles come, etc. So aggregate moves. What can you say about motion of rightmost particle of the aggregate? This is rightmost particle in dimension 1. And already in dimension 1, it represents highly non-trivial behavior. So there are 3 results. So first result was done by Harry Keston and myself in 2008. And it tells that if density rho, so I differ now, rho stays always for version of random walks, it's Poissonian parameter, and mu will stay for exclusion process with Bernoulli parameter mu. So if rho is smaller than 1, then RT, what is written on slide, asymptotically behaves as constant, which depends on density times T 1/2. So it grows sublinearly, aggregate. Okay? This, what is written here, is, I will explain in a minute. This is relatively soft argument which involves CLT in both cases to show that it's not faster and not slower. Okay? Then if rho, still everything is important, dimension is 1. If rho is 1, then R of t behaves asymptotically as some constant t to the 2/3. So this result with Balázs rod, but actually still have many places which have to be fixed. It's not really a theorem to state. But so we have article on arXiv, so it's sort of how to say, mesoscopic level analysis, which suggests that it's true, or shows that it's true, if you start from mesoscopic. But how to go from microscopic scale to mesoscopic brings us serious headache. So this is 2008. This is with Balázs. We actually did it in 2015, but it's still there. And finally, third result, rho bigger than 1, then rightmost particle behaves asymptotically as C, which depends on rho, linearly. So this is result obtained by Alan Sly in 2016. So it uses multi-scale argument, which I will talk about it. And actually, it works in any dimension. And in any dimension, I think you could go even below 1. And this is, so in dimension 1, this shows that critical value is 1. So for any rho smaller than 1, you go sublinearly with square root. Here you have this, and it has nothing to do with KPZ for the moment, but it will, this model will have to do with KPZ, I will tell later. And then finally, this grows linearly. And if I could say, this is a soft result, this is not finished result, and it's actually very hard kind of multi-scale analysis here. So, okay. So one question which you would like to ask, even in one dimension, there is no geometry, guide goes linearly online. But you can ask, what is the density of the Because sometimes, in order to make step forward, you use only one particle. And sometimes you use 3 particles. So, especially in this case, so this case I will explain to you just in a moment here. In this case, there is some very interesting question which I don't think we understand completely. It's sort of self-organized. If you consume too many particles, and you advance at a higher speed, because if you have pile of n particles, so rate at which you will advance, at least 1 particle jumps, but you consume 10 particles. So something which is in front of you lost some density, so you need to wait a little bit longer than when particles come. So this is very interesting to just to understand, not only that it grows linearly, but how dynamics is built. So let me call on enemies. So who really, not that I know, there is no, well, I mean, at least the way we look at it, you will see, I will explain what is the mechanics of story. And of rho smaller than 1, what I say, things are soft. Rho is smaller than 1, so this result with Harry Keston. And essentially, to understand that this is happening, intuition is pretty easy. So you aggregate particles. Doesn't matter. So and this result holds for both models, for random walk and exclusion particles. So you can take exclusion model. Of course, exclusion model doesn't have more than 1 density, and then you start to build cluster. I don't really care about internal density, but here's RT. And I claim that RT is of order square root of T. That's the result. So how we prove? We say, suppose it is not. Suppose you are, this is false, you are T half plus epsilon, right? Suppose. Okay, good. But if at time t you are at this distance, in order to make 1 step, you need to have at least 10 particles, 1 particle, right? So in order by time t to have t to square root of plus epsilon, you need to have this number of particles, right? But where are they from? So if you look at this distance, and this distance is t 1/2 plus epsilon, right? So you need to have here this many particles, but they're distributed initially as Bernoulli or Poisson. So in order to have these many particles, you need to look somewhere. But how particles from distance like that can come and glue to me? Just central limit theorem, you cannot. Okay? So this part is completely, you need to make it kind of technical, but it's kind of really soft. Now, suppose it's opposite, minus epsilon. This requires some technical work, so if you are shorter than what you expect, how can you get this particle incorporated, and where other particles which would bring you by time square root of t out? So you need to prove here that you typically do not incorporate too many particles on average. Then you get this. You cannot be smaller than half. Is this making sense? At time 0. By time t, typically, who is coming to you? Particles which are standing at distance square root of t. Particles which are beyond, they typically don't come. So you have these particles in distance square root of t, they're hitting you. One, another, maybe a couple of them, okay? So how you can now deteriorate the square root of t, which are coming, by sort of over-consuming particles. That suddenly higher order than square root of t will come together. And suddenly you get some extra block and something extra block, which suddenly diminishes. This is technical part, but again, it is soft part, to show that events that you are consuming more than some number k of particles per step, it's unlikely. Yes? Okay. Anyway, it's sort of soft argument to do it. I'm not saying it's totally for free, but just to give intuition. However, now, in case of paper of slide, difficulty is completely different level. So rho is bigger than 1. And then, just to give an argument, it's very complicated multiscale. Well, I still find it beautiful, but very, very complicated. So think of you having rho much, much bigger than 1. So you are overcrowded by particles. Okay. What do you see? You have aggregate at time 0 and tons of particles everywhere. So if I can say you have carpet of zillions of particles, suppose rho is large. You have zillions of particles, and then when you see this carpet of particles, so everything is easy, life is easy, because one of them jumps, you move, one of them jumps, you move. These particles perform random walk. Random walk is, in principle, nice behaving, as long as you don't know that somebody is coming to eat you. So all these particles are happily, moving as random walkers, right? And then you advance linearly. Nice. No matter which row you take, eventually you will see gap. There are no particles. What happens? Come nicely to this border, and what? Nothing else happens. So, but still, here you have lots of particles. And these particles are random walkers, so they are diffusing here. So you're not going to be stuck forever. You will wait until Salvatore is coming and move you by maybe first particle comes, you move, then second particle comes, you move, then 3 particles come, you move, etc. And you start to pick up velocity, not velocity, but you start to pick up. Okay? Until you find this carpet, but a little bit diluted in some situation that now, here you had everything according to rho, and your speed is according to rho. But now you got diluted things, so it slows down. Okay? And now you would like to say that this slowing down is not going to really slow down to some velocity, which is strictly smaller than original velocity here. And then you move, and then you find smaller gap and other. So you want to prove that actually performing this motion, you do not go to 0. So you need to somehow ensure that all these scales of obstacles don't really stop you below some line. And that's what Alan did. Alan, you can correct. I'm interpreting rightly. So exactly, enemy is now kind of big holes. Well, holes of all type, actually, not big holes, because big hole gives you strong punch in dropping velocity, you get stuck. Intuitively, it's very easy to see that these guys, if you are distributed initially with Poisson product measure, they're exponentially rare. Okay? They're exponentially rare, kind of guys of size L. Sort of. See, I see. Exactly, that's the, and also, to like this, it's just artistic image of big hole, because you have many smaller holes clustering, so you need to do all this kind of delicate analysis, like zillion separated small holes may actually give you trouble bigger than one beacon like that hole. But if you just put some intuition inside, so these guys are exponentially rare, and even clusters, which I can interpret as big guy, are exponentially rare. Okay? And then you think, okay, if this happens, from this source of particles, because this is overcrowded, it takes for you, suppose this size L, it takes time L squared to cross. So your Salvatore comes in time L squared, you move, then another comes already time less than L squared. So if I will be very generous, it takes for you L squared for each particle times L cubed to cross. This is the worst possible estimate, kind of primitive estimate, right? So if you have some kind of obstacle which appears exponentially small in L, and to cross this obstacle, it takes time L cubed, so why we should worry, you know, you still keep velocity. But point is that it diminishes you, it slows down you a little bit, but then there is some dust of smaller guys, it also slows down, and then when you meet next guy, you need to be sure that you are in good shape. So that's exactly where multiscale of Alan tackles these things. And not only, so this is very clear intuition when rho is 1, and proof of Alan goes to 1. And this is a very interesting moment, because before we knew this picture in one dimension, Ronald Dickman, who is expert on very precise simulations, actually he did it for us. And what was interesting that from his simulation, he exactly predicted that rho smaller than 1 behavior exponent is 1/2. And he predicted also from his simulations that if rho equals to 1, behavior is 2/3. But then he started to say us that something strange happens above 1, that actually constant, where you become linear is not 1, which now is a fact of life, but is bigger than something like 1.4. And between 1 and 1.4, system undergoes multiple transitions that you get from 1 smaller than 1/2 to here to third, but then between 1 and 1.4, you have like various regimes that you get a little bit faster than to third, but still smaller than 1, and then goes and goes and goes and goes. And it was kind of, and it took us, before Alan came with his proof, a long time. I would have days that I would say this is correct, because if you have density 1, you have to consume particles one by one, essentially, to move, because it's kind of particles. So it's very kind of clear that at 1 you cannot be linear, because eventually you consume 2 particles, and this density drops down. But here was very interesting question, which now is solved. So we have now a really sharp transition between sublinear, linear, and 2/3. I would expect this, but we have no proof. Yes, so there is observation of Tom Kurtz back to, I don't know, maybe 10 years ago when we started to work with Harry, that when aggregate moves, no matter which density you have in front, sort of evolving quasi-stationary distribution. So, and when rho is smaller than 1, this distribution is sort of vanishing. That's why you are sublinear. Now, in the case of Alan, you have, can we call it sort of stationary, but it's a product measure. It's a product measure, but it's sitting in front of you, etc. But density changes.
density in front of you is, you sort of control that, and you can find sort of regeneration times at which you, what's happening in front of you. And, but the sort of, the density right in front of the aggregate tends to be small, and that's why you don't run into multiple particles very, very much.
No, but skinny, when rho close to 1, then it comes skinny. But when rho is huge, then it's sort of less skinny, let's say. Okay, let me move. Some more questions? Okay. So that was story of, yeah, that's exactly open problem what you asked. So what is the, how skinny is skinny? Yes, so now Lance argument for random walk case works in any dimension. So it tells, but what means in any dimension grows linearly means that if you look now, I will show pictures in a minute, but if you look now at aggregate, it's kind of two-dimensional object, right? So this result says that if you look now, you know, it's kind of like in DLA, it has arms. You know, here, 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 and then the farmost point. So every arm has its farmost point in all among this arm. Look, the farmost grows linearly. So it means that it's not that one arm necessarily grows linearly, but this guy now is leader. And then after a few seconds, this guy is advancing. So rightmost particle is now object differently from one-dimensional case that you have. It's object which jumps. It's like in Tour de France, you have leader wears yellow shirt, and then from day to day, leader may change. So in this case, proof along guarantees that yellow shirt guy always, though you close your eyes and open after 5 seconds, it's another yellow guy. But all of them, if you look modulus of things. All right, so let us go to dimension 2, and then and I am now switching to original model. And the reason to switch for original model, it's attempt to see that this DLA type Rose model, at least for high densities, has chance to be actually KPZ type guy. So, so what is important? I go back to this exclusion rule. So density of particles is no more than 1. Okay. Observe that even, well, that's kind of trivial observation, that in dimension 1, and now I put restriction exclusion. So you cannot have density of particles more than 1. Okay? And the result with Kesten says that if rho is now exclusion, we have mu, because it's initially distributed as Bernoulli, so mu strictly smaller than 1, then we know that aggregate grows sublinearly. This theorem which says no matter how close to 1 you are, you're full of particles, you will grow sublinearly anyway. Though in paper it's written for random walkers, but it just goes straight. But just kind of simple observation. Imagine mu equals to 1. Mu equals to 1, and you have exclusion rules. Nothing to do, but so you have aggregate, and you have white particles. Which are still white, and they cannot move because it's exclusion, they are blocked. But I still can define propagation of red, because all these particles are sitting. This particle wants to jump to the left, but it's suppressed. This particle wants to jump to the right, it's suppressed. But this particle also wants to have, may have wished to jump to the left. And then I say, okay, this is aggregate, these are not aggregate particles, and this guy becomes red. And then eventually this one go. So you see, it's what? It's first passage percolation on the line. Yes? So there is transition kind of in some naive way that, of course, it's first passage percolation on the line. So rightmost red particle is at distance t. Agree? So here is the birth kind of role of first passage percolation. Just to give you kind of naive example that FPP somehow could be a point of change. So now we go to dimension 2 exclusion rules. And here are simulations done by Stauffer, Alexander Stauffer, who is in transition from Baus to Rome. So this picture, yeah, so this is on the lattice, and then I will comment because lattice confuses us. So let me show quickly 3 regimes. So it's very low density of particles. So this simulation took very long time to produce this picture, and it resembles in some way usual delay picture on the square lattice. You have influence of axial direction, but actually we don't believe it is close to DLA. Then if you increase density of particles, so this is low density, cluster gets more shapy, sort of, like going to something. Still you, I don't know if you can see, maybe I can switch some light. So that was low density object, sort of medium density object, but it's already start to get around the shape, because at low density, you see it sort of reminds you possibly losange in some sense, but still has very ramified structure. And then question you may ask, if you look at this object and you look at some branch of it, do they have the same behavior? It's kind of sort of fractal type, fractal, which I would understand that at any scale you have something similar in distribution. So now it changes, but still you can see that this fjord type structure is present. So it's not so ramified as small density that you have very, very long and clearly open sinks areas. Now you have kind of shaped guy, which definitely looks like having density. So Hausdorff density of usual DLAs, at least in dimension 2, expect to be 1.7, 1, I don't know how precise it's known. But here it's kind of clearly seen transition from possibly density smaller than 1 to density which looks like already has positive density. And finally, if I increase number of particles, you have even more roundy shape, but still, I don't know if it's possible to see, but you have kind of fjord structure. So you see, if I put a box here, I can see that these fjords are converging to some point, and I can detect where is a seed. So now we are sitting in regime of exclusion particles. And again, so this is very high density, very high density. So suppose density is 1. Exactly by the same argument, maybe we can put light. By the same argument, if density is 1, in any dimension you get FPP. Okay? So question is, you start is this clear? That if I look at this model at density 1, it's just FPP, so you have what I want. You have this KPZ, supposedly, we don't know how to prove, but it's for spatial percolation. And then suddenly you just diminish a little bit of density, so you have particles absent in some sites, but it's very few. And these empty sites, actually, by duality of exclusion process, they move as exclusion process, empty sites. So does it affect you from going from FPP to something else? These impurities which are moving. So now, if impurities were static, there is classical result by Vandenberg and Harry Kesten, which says if you look at FPP with some defects, no matter how small they are, no matter how rare they are, you will drop velocity. Velocity will be strictly smaller than without defects. So now I'm moving from rho equals to 1, which is FPP, to rho, which contains particles, and they are not static. They are moving around. Okay? How much it affects you? How much this evolving cluster? So now, imagine you have a situation that you have aggregation process which has very tiny percentage of holes. These holes are moving and they are rare. So at the beginning you start to move and everything is fine because you feel like you are FPP. But then there is finite and integrable time, you knock on first hole. What happens? And happens something which very unpleasant, but still not as unpleasant as Alan's case. Because in case of one dimension, okay, when you meet a gap, you have no choice. You need to be rescued from this gap. So you need to wait Salvatore coming and saving you. And, but in two-dimensional case at high density, what happens? You met a hole, it blocks because you cannot advance, or you can meet cluster of holes. You cannot advance in this cluster because nobody pushes you, right? But you can go around. So if these objects are rare, then situation becomes sort of difficult, but not as unpleasant as in one-dimensional case. So aggregate is growing, so it's red cluster. And then you have cluster of empty sites. Empty sites by themselves perform exclusion process among themselves, right? But once you construct aggregate, it's stuck. You cannot penetrate aggregate with holes. So holes are free to move here, right? And difficulty now comes that you cannot really let holes inside. So you're like, I don't know if you know word bulldozer. So you start to push these holes from one side because holes suddenly start to get slight drift away from aggregate because they cannot go here. So every time you want to go, you cannot go, so you go somewhere else. But then because of this exclusion rule, you have chance to encapsulate. So this guy grows faster than these holes are moving, and you encapsulate holes. Okay? And then this problem is solved, except that this problem appears on all scales, like in one-dimensional thing. So, and now by Harry Kesten and Vandenberg and Harry Kesten result, you know that if holes would not exist, you would have asymptotic speed of cluster. But now, no matter how small density of holes you have, by Harry Kesten, Vandenberg and Harry Kesten result, you know you are slowing down. So suppose you would have hardcore interaction. I do not allow these holes form clusters. There's not only exclusion, but I say holes cannot come to each other closer by distance r. So you don't have this type of multi-scale. You have just single holes, and when they appear, you kind of encapsulate, 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 etc. So kind of easy job. Everything is easy to prove if I put this condition, except that it drops velocity down. Present. So your aggregate, which is in pure no-hole situation, would move with velocity v. Now it's moving with velocity v, density of holes, and depending how far they are from each other, etc. So, and then comes double, triple holes, etc., and everything is pushing you down, presence of them. So question is that if you don't have any restriction of distance, is this velocity still positive for this guy? And is this problem clear? So it took us with Alexandre quite a long time to understand how to deal with these holes, because they are not static, they are moving somehow. They are moving actually like random walks with certain drift, because you are not allowed to go in. You always have to go out. And then comes a model, and now we are drifting towards KPZ. I introduce a model which stochastically bounds spread of aggregate in certain way. I will explain. So two types. FPP. So it's not a new sort of situation for people who study first passage percolation. So you have two types of first passage percolation. So it's classical result started with Hegstrom and Pimentel. So if you have two types of FPP, seed of one FPP is here, seed of another FPP is here, and they start to develop as FPP clusters. And if site is taken by red, then white cannot take. So you have kind of boundary. So this is red world. Oops. This is white world. Oh, the most interesting part is gone. So, and question is coexistence or not coexistence. And it's known that if speed of, I just take 3 minutes more, and speed of both of FPPs is equal, there is coexistence. So Chris has even more sophisticated results for many colors, right? I don't know which number you have. 4. Okay. So, but now question is, if one is faster, another is slower. So one is faster means that somehow is more powerful to get territory, and but also slower, it's kind of, if distance is fixed, you have positive probability encapsulate big one, and that's it, it's done. So it's not like David wins against Goliath all the time, but he has a chance. And then the results of, so what we use, okay, so this main theorem which we have with Stauffer. So look at this picture, or that picture. So you have some fjords and you have non-fjords, and things could be encapsulated. So you don't see very clearly here, but this fjords continues, but eventually they will be closed. So it's not trivial fact, because it could be that you start to do fjord, and then somehow it's very difficult for particle arriving here to make closing. So theorem says, if you look at aggregate at high density, so this theorem is going to the limit of being close to 1. So exist density is so high, such that if you look at the aggregate, this is an aggregate which you give. And then you look at set aggregate bar, which means set of vertices which do not necessarily belong to aggregate, but A bar, this in red, contains all vertices which are in aggregate, but also vertices which are not in aggregate, but which do not have infinite paths connecting them to infinity. So means all these kind of bubbles which aggregate closes. They are not in aggregate, but they are already, so if you look at this AT, that's object of the theorem. And then there exists mu large enough, means close enough to 1, that AT contains ball, there are constants C1 and C2, such that AT contains ball with probability C2. This C2 should be 1. And problem not to be able to put 1 is a technical condition because initial configuration could be so bad, but eventually you will beat it, but we cannot prove that. So this actually constant should be probability that AT contains ball for all t, eventually it's equals to 1. We cannot prove, we can prove that exists C2. But this is not really conceptual, it's technical, okay? So that's a theorem, and it's, we don't put on the other side because this part is contained in the ball is trivial. And so that's the main result. And just to finish, we introduce first passage percolation, which is very interesting for many aspects. Actually, this model is very interesting by itself. So we have two types of percolation, first passage percolation. One starts from the origin, red one, and then you have seeds of second first passage percolation. And this object starts to grow. And these guys stay still, they don't grow. This second type of first passage percolation until they are activated. So when red cluster comes to the nearest neighbor of yellow, yellow starts to move. And then it grows, it competes with red. Maybe it slows down red, but maybe red is beating it somehow. Then you come to another yellow, and then you have this enemies. It's like traps of poison for cockroaches. So community of cockroaches are growing, but then they meet some poisonous guy, and then it slows down, but maybe cockroaches win, but maybe guy wins locally quite a lot. So these poison traps, at time 0, they're doing nothing, just staying there. But as soon as they activate it, they start to move. Okay? And this object gave us a lot of surprise. So first of all, it bounds this trap, it bounds in its behavior movement of single empty site. And because when you grow, empty sites actually don't know where they are. So you always can think that outside, so it's somehow Markovian evolution of boundary of red until it meets yellow. So you know how yellows are distributed. And then if yellow wins, means cluster dies out. Red cluster stops growing. If density of yellows, that's a theorem, is very small, then red cluster wins. So every yellow guy will be eventually encapsulated. So red cluster has infinite component and no yellow infinite component. That's a theorem. And this theorem actually is based on multi-scale analysis. So this is a scheme of encapsulation from Hegström and Pimentel. So how you beat actually, even this guy is very slow. It can grow. And then it meets a seed of very high speed. And then if this guy is big, the seed has chance to be encapsulated. So how black color evolution can beat yellow? Yellow is slower but bigger. And then tactics comes from sort of military technology. You just retrieve. You start to go back, actually. Black doesn't attack. Black starts to go back, getting bigger, and then finally it wins. So that's exactly essence of proof of Hegström and Pimentel. And then we use this technology. We need to improve estimates, and essentially, multi-scale is just, I could write exact scales, etc., but makes no sense. So you want to say that if you start from black spot, then eventually you successfully beat everybody at all scales. That's the essence of proof. What is really intriguing of behavior of this new percolation, first passage percolation, that if density of yellow guys is very small, then black colors are getting shapy, and that's possible relation to KPZ. So it's expansion in this black color FPP, and then obstacles produce you kind of damage. But what was much more intriguing and interesting, that at low density you start to get figures like that. It's coexistence of black, which is colorful here, and yellow, which is, I don't know if you see this tiny line. So this tiny line here, it's boundary what yellow taking. And we did a lot of simulation, Alexander Stauffer did a lot of simulation, and we start to observe something interesting, that typically for people who work in interacting particle system, if you have some growth process, it has to kind of spread linearly. That's a very classical result. So if you don't spread linearly, then you are in danger. And here suddenly we see behavior like these branches, and it looks like it starts to spread. But if I would continue, I have many more simulations. Suddenly this dies out and yellow dominate, and this becomes tiny, suddenly gets explosion, and these arms are growing in a way that doesn't look linear at all, spreading. So there are no kind of shape-like theorem for branches here. So there is example of Schoenmann, Duret, Bramson, Duret, and Schoenmann, of kind of contact process in random environment, which survives non-linearly, but it's a very special case. This random environment is rather orchestrated to produce this result that you are not linear. And here it's kind of situation which very interesting to map. And yeah, and I think it's right point to stop.